Margarita Sordo. Margarita is an artificial intelligence and medical informatics researcher and an instructor of medicine at the Brigham and Women's Hospital in Harvard Medical School. She has a master's degree in artificial intelligence from the University of Edinburgh and is a PhD in computer science and artificial intelligence from the University of Sussex, also from the UK. And Dr. Sordo is also an elected fellow of American Medical Informatics Association. Currently, she is an appointment representative of Mexico to the OECD Global Partnership on AI, and she serves as a member of the steering committee on AI for pandemic response and of the AR for drug discovery too. Margarita research is focused on a lot of fields, but mainly we can highlight AI and knowledge representation for clinical decision support, data governance and responsible use of AI, and complex adaptive systems to model patients' characteristics and preferences and to evaluate their potential impact on patients' health. So welcome, Margarita. It is an honor to have you on our conference. If you want, you can start with your presentation.
Thank you so much for the I was getting a message here. Yes, thank you so much for the invitation, and I'm happy to be here today with you. And okay, can you see the screen?
Yes, we can.
Okay, so today I'm gonna talk to you a little bit about knowledge-based AI to support the practice of medicine. And before I jump into that, just to add a little bit of to what you already mentioned, when you introduced me, there are different aspects of medical informatics, which is what the application of AI and computer science techniques in medicine. So but at the core of all the things that we can develop is, it's always the patient, the health of the patient, the well-being of the patient. So from this perspective, and throughout my career, I have worked in different areas that well, I would like to think positively impact the well-being, the health of patients, and also will help clinicians in the practice of medicine. So some of them are knowledge representation and artificial intelligence that then can be translated into clinical decision support, and knowledge discovery tools have developed national and international standards for representation of not only data, but also knowledge that could be shared among different institutions throughout the world. I have applied artificial intelligence techniques for epidemiological studies, incorporating determinants of health and also modeling patient behavior, this to detect signals in patient data in the general population, and also for knowledge discovery. And also, well, understanding the clinical workflows and needs from the physician's point of view, in order to develop applications that actually satisfy the needs, the requirements, but from a medical perspective. So why is this important? Because if we think that the practice of medicine is actually a problem-solving activity, that requires to have reliable patient information and up-to-date medical and clinical knowledge. So when physicians are interacting with patients, they are gathering information through questions and looking at the patient records, and where does it where's the pain, how do you feel, when do you feel it, blah blah blah. And then they start going through cognitive processes, like they start with, let's say, with all possible diagnoses, and they start narrowing down the options through this questioning and applying knowledge. So they are also answering internally questions like, okay, no, these symptoms don't apply to this disease or these problems. So they start eliminating things until they end up with, well, ideally, one diagnosis or 2 or 3 potential diagnoses, and then they take actions, in the form of, ordering lab tests or doing some procedures or something, just to figure out what the problem is. So the purpose of medical informatics is to systematically provide, the tools for clinicians to discern how data and knowledge are interconnected, so they can actually solve the problem, of treating a patient and providing the best quality of care. So for this is necessary to have, information and knowledge at the right time and in the right format, so whatever tools we develop actually help, physicians in their practice of medicine, instead of disrupting all the workflows they need to follow to find answers, when they want to treat a patient. So and they can make obviously the right decisions, and not just for one patient, but for every patient. So we, in summary, we say that, the providing this clinical decision support, in a nutshell, is we need to present all that information, that knowledge that is important to remember, at the right time, but it's easy to forget. So when I say that we need to have a knowledge-based approach, what do I mean? I mean that we need to understand the problem from a clinical perspective. It's not ideal that when we talk to a physician, because he or she wants us to develop something, that we immediately jump into selecting an algorithm and like, oh, okay, just give me the data, I'm gonna put it in through an algorithm, and I'm gonna give you something, and that's it. No, we need to understand the clinical need, from the perspective why that problem is important, how if they didn't have the tool, how would they solve the problem? So we get into these cognitive processes, we get into the clinical thinking, if you will, the problem solving process they are following, and we need to understand that, so we can see how they think, how all these the engines move. So what we develop actually aligns with that, and by doing that, we are already providing some transparency to the process, which is important, because we need to develop things that are transparent and understandable, from not only from the computational perspective, but also from the clinical perspective. Once we understand that, then we can identify, gather, and prepare the data we're gonna need. Then we can select the algorithm, because they are many powerful algorithms, but they don't work all the same, and they don't provide the same results. It's important that we avoid bias, and that goes to understanding the problem from the clinical perspective, understanding what's the from all the patients, in the universe of data that we can have, where are we going to focus? For example, adults versus pediatric patients. So we are already dividing all those patients into 2 different demographic groups. Are we going to focus on women or men, or it doesn't really matter? And if we put them all together, what are the differences? Because, well, just a quick example, in terms of, for example, measuring cholesterol levels or managing cholesterol levels, the recommended range is different from men and women. So we need to keep that into consideration to avoid any potential bias. If we train the algorithm with only, let's say, only women, and then we use it for men and women, we're gonna get some results that really don't, are not correct. And we need to understand and review, the outputs and the results. It's not enough that we create the algorithm, we got this input, we get this output, fine. No, we need to understand, again, not only from the computational part, that the algorithm and the process is sound, but also from the clinical perspective. And for that, we need to stay close, and interact closely with clinicians, with the people that are going to use this algorithm, so we can validate our results. And we should be able to explain and present, present and explain the results we get from the algorithm. This is part of the validation process. Ideally, and I'm going to show a slide where we can actually get explanations or supporting facts when a recommendation is given by a system. That's very important, because that goes to just showing the transparency of the process, but also providing supporting evidence, and so we can eliminate as much as possible or mitigate the effects of having a black box as the algorithm, or the like magician's hat, where we get the rabbit out of it, but we don't understand what is actually happening inside. So in addition to that, we need to have a knowledge-based workflow, and for that, as I already mentioned, we need to understand, the first step is to understand what the research question, or what the problem we want to solve from a clinical perspective. And for that, we need to interact closely with clinicians, because we need to get, to understand it from their perspective. Once we understand that, then we need to move into define what the cohort, as I already mentioned, with the example adults versus pediatric patients. What are the characteristics of the people that from which we're going to get the data that is going to go into the algorithm to provide some recommendations. So we need to understand the target population, what we want to measure, obviously, what's the outcome that we expect, and how we're going to make sure that the algorithm or the tool works correctly. Once we've done with that, then we can start looking at the patient data, because then we need to see, like I said, for the pediatric versus adult population. Okay, I'm gonna focus on adults. Okay, what's the data element from the patient record that is going to allow me, to separate, to filter out the pediatric population, because I only want to focus on adults. So for that, obviously, we're gonna need the date of birth, and we're gonna need a threshold value that here in the US is 19 years old, to distinguish a pediatric patient from an adult patient. Once we identify that, then we can translate, those the data extraction criteria into what we think of, we have our data in a database, an SQL database. We can start translating that into executable queries to start getting the data that we're gonna use, that we're gonna need, to train the algorithm. Notice that we are on step 4, and I haven't mentioned, I'm not there yet, that we need to pick the algorithm, because there are still other things that we need to do. Once we have the queries, then we're going to extract data, and we need to identify the sources where we're going to get the data. It's just going to be phenotype data that is going to come from the patient record, that we're going to use genotype or endotype data. Are we going to get the data from a single source or from multiple sources? Because if that's the case, then we need to clean up the data. You know, we can have, for example, here in the US, height is measured in feet and inches, but in Europe is measured in meters and centimeters. So if we're going to have data, let's say from the US and Europe, well, we need to reconcile, because we cannot put, you know, like a 5'3", you know, next to 160 meters, 1.60 meters, even though they are equivalent, but the units of measure are different. So we cannot just dump all the data together and then use that to train our algorithm. So we need to reconcile, normalize, validate. So what are we going to do if we have missing values? You know, we're going to remove them or not? Or, you know, what's going to happen? So we need to standardize, clean up the data, and then, depending on what the research question was or what the clinical need was, you know, step one, then we're going to select the algorithm that, you know, mostly satisfy that need, or that could answer that research questions. And then, well, we can add other things, you know, for visualization, to identifying trends, and so on. And through the process, since we've been interacting closely with clinicians, once we have the answers, we can have a pretty transparent process that we're going to allow us, and are going to allow clinicians to validate not only what we are getting from the algorithm or from the tool we are developing, but also we can identify new knowledge that maybe we didn't know at the beginning, and that knowledge could be fed into, you know, the initial research question, and maybe repeat the whole process, you know, until everybody's satisfied. So how we put this together? So I think that the essence is we need to be clear, or this would be the question, what problem we want to solve. So here I have an example where we gather, so we gather clinical, patient, and genomic data from patients that have renal dysfunction and heart failure. So we're gonna get information from, you know, the patient record, like lab test results, history of, family history of, if they have problems of cardiovascular disease problems, some demographics, vital signs, etc. Some the clinical context, it's also defined. We're gonna use genomic information. We're gonna incorporate that. We're gonna follow all the steps I mentioned before. But the problem, you know, going to the problem we want to solve is, we want to see if the renal dysfunction or renal problems is a consequence, or is the result of having heart problem, you know, because then when people start having problems, you know, the fluids in the body and the kidneys are not processing everything in the way they should. So they're gonna start, because of the problems with the heart, they're gonna start having renal dysfunction. So even though the data we gather, you know, from all the different sources might be the same, you know, it's like, what's going to be the input, you know, to our algorithm or to our tool, and what's going to be the output. So if the renal dysfunction results from having, it's a complication of having heart problems, then what probably we want to classify is, well, the different stages of renal dysfunction. But it could be the other way around. It could be that, you know, the patient has renal dysfunction, and as complication of that, they start having, heart problems. So again, it might be the same data that we're going to use, but then depending on the problem that we want to solve is what's going to serve as an input, what's going to serve as an output, how we're going to validate where we are getting. So just quickly go through some examples of some applications that I've developed over the years. The first one is a knowledge-based neural networks. And the problem we want to solve is, well, it's a classification, but also we would like to have an explanation, because normally, neural networks are, infamous for being black boxes. So yeah, we present an input and we're gonna get an output, but we really don't know what happened inside, because, well, we have many connections, many weights between the nodes. And it would be better, if we could understand what happens inside. So in this example, we're going to integrate knowledge from existing knowledge from the literature into the structure of the neural network, and then train the network with data. So the advantages of this, the specific example is, we want to distinguish breast tissues, the activity of breast tissues throughout the menstrual cycles. So this is for premenopausal women, because the breast is very sensitive to changes in hormone concentrations, and the cell activity in the breast, changes throughout the menstrual cycle. And this activity, there are 4 phases of the menstrual cycle, and during one of the phases, cell activity increases. It could increase a lot, and sometimes this could be mistaken by some abnormality, that cells, breast tissues are abnormal, because increased cell activity is also characteristic of cancer, or in this particular case, of breast cancer. So we want to distinguish that, and we use the data is magnetic resonance spectra from normal breast tissues from premenopausal women. So we incorporate, existing knowledge into the structure of the network. So the links are connected, and they are labeled because they represent something that has been extracted from the literature. And then the neural network is trained with a small data set. This is also useful when we don't have many cases, much data to train our algorithm. And then we're going to get some, the classification, which was the purpose of this, a classification of, this is just 16 cases of breast tissues into 4 phases of the menstrual cycle. But also by analyzing the weights at the end of the training process and the validation process, we can see which connections are more relevant. So that helps us understand, not only getting an answer, but also understand what's happening inside the network, and we can extract those that knowledge that then we can translate into explanations, to support what the result we are getting. Another example goes, this is again for breast cancer diagnosis, and this is for the CDS integration. It integrates all the different aspects of its knowledge from neural networks, from symbolic reasoning, all integrated into the workflows. It also takes into consideration contextual knowledge. And
sorry, Margarita, only for letting you know that if you can have your talk in 2 minutes, 1 or 2 minutes.
Oh, okay. So I think I'm gonna finish this one, and that
Okay.
would be it. Yep.
Thank you.
So here, what we have is what mammograms, X-rays from the breast that have been, processed, and instead of using, deep learning network, something like that, is going to identify potential abnormalities and is going to highlight them, but without any explanations. We break them down into, a couple of more steps. So the image is processed, abnormalities are identified, and then what we're gonna get from that, the image processing, are just numbers. But if we think that, for example, 0.34 is corresponds to the size of the abnormality, well, that doesn't say much, really. Think of when I mentioned that, the cognitive processes physicians follow, and what they do is, what they look at a mammogram, identify abnormalities, and then characterize them in terms of size, shape, density, and location of the breast. So having 0.34, instead of having, for example, size is small, size small, it aligns better with the way they think, the way they reason, than having a 0.34. So what we get from the image, we use, intermediate neural networks to map numeric information into symbolic representations, so size, shape, density, location, that then in combination of patient data are consumed or are used by a clinical decision support application that follows the workflow, of gathering clinical history, analyze the mammogram, and then provide an assessment decision or recommendation, and then actions that could be followed. So in this case, this application provides the assessment saying, okay, this particular abnormality is more likely benign, and the supporting evidence. So again, there's transparency and explanations present. And also those explanations are in a form that it's easy for them to understand, and they, and consume immediately to move along, the process of making a decision. So we would get that, the size is small, the shape is round, the density is low, and the location is mid-breast. So that aligns much better with the way physicians reason and process information, and makes the use of this tool, more seamless. It could be much better integrated into the workflows without actually disrupting them. And I think I'm going to stop there. I have, a few more examples, but I think I won't have time to go through them. But I'll stop here.
Okay, thank you so much, Margarita. It was an amazing talk. I really like it. I love your explanation of the knowledge-based workflow. I think it is very, very useful, not only in this area, but it is applicable for a lot of areas. So thank you so much for being here. I think we have a question from Leda Carolina Torres Maldonado. She said that it was an excellent talk. She's congratulating you. And the question is it possible to have an algorithm to search phenotype-genotype correlation in diseases with genetic heterogeneity?
Yes, it is possible. I think it goes to breaking down the problem. What I showed at the last slide, how well, I'm gonna make the analogy with the breast cancer diagnosis. You break down the problem, instead of having just one tool that is going to solve a big problem. You can break it down into smaller intermediate problems or tasks, and for each you select an algorithm or some computational technique to solve that particular smaller problem. And by doing that, instead of having, you know, a big, huge problem that it's sometimes even difficult to grasp and understand, when you break it down into smaller ones, then the context is also smaller, you know, more you know, constrained, and then it's easier to understand and to find a solution for that little problem, let's say, that then when you put together with the next little problem, you start building like a tiny chain, you know, that eventually is going to solve the bigger problem. But you have on the understanding, you know, at all the intermediate steps, or all the smaller problems. So yeah, it is possible. You just have to break it down, understand again what's the contextual or the clinical need for that smaller problem, you know, interact closely with the clinicians, the researchers that know a lot more about that. And then when you move to the next one, then you still gonna need to connect them. So for that, you need to understand both, you know, the first one and the second one, and how you're gonna link. And that goes to when I mentioned that, okay, we understand the research question, and then we move into identifying, you know, the phenotype and genotype and all the information that you need from the clinical perspective, you know, before jumping into, you know, because just to give an example, if we want to, for example, follow up, have something that follows up diabetic patients, well, we need to understand that, you know, there are metabolic abnormalities, you know, depending on what type of diabetes we are talking about, but there are metabolic abnormalities that we need to track. But that's a kind of the conceptual topic. But then what kind of data do I need? Oh, well, if we're gonna track that, well, we're gonna maybe need, you know, measure some, you know, insulin levels. We need to measure the HbA1c in patients. We need to check the diet, exercise, what medications they are taking, whether, you know, how those medications actually work. So we started getting into, you know, something that is a little bit more specific. So, oh, okay, so if I need to get the HbA1c from patients, oh, okay, I'm gonna get them all, or I need to focus, for example, just fasting, you know, HbA1c, or it could be, you know, they are not fasting, because that's going to change. So that's the information that we need, but then we start, you know, breaking things down into smaller parts that then later we can integrate.
Yeah, sure. Thank you so much.